Hey Vanguards, it is time for the, the fifth lecture on the Schrodinger model. So I think there'll be one more after this one. So let's see what we can do. Today we're going to talk about valence electrons and exceptional electron configurations. Alright, so you can get this PowerPoint on the pickup file, so make sure you're looking at that and have a periodic table with you while you're looking at this. Okay. We're supposed to draw every single atom using this giant chart, but that takes too much time, so we shorten it to the box method, but that takes too much time too, so we shorten it to the electron configuration method, 1s2, 2s2, 2p6, and we write out the whole thing. But wait a minute, sometimes that takes too much time, so we use the noble gas notation. So for these great big giant atoms like this one, we figured out, well, what's the biggest noble gas inside of there? And they all end with P6, something or other. So this one, if I go backwards, I say, oh, there's a 4p6. Let's see, what is this? All this stuff in here, I can just ignore that. And 4p6, look at the periodic table. Krypton is in the fourth row down. And so instead of writing 1s2, 2s2, blah, 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 all the way up to 4p6, we write down Kr, put it in square brackets, and then we figure out, well, what's this atom? How much bigger is it than Krypton? And it turns out that this one is 10, 11, 12, 13, 15 electrons bigger than Krypton. So Krypton ends in a 4p6. What comes after 4p6? Oh, that's 5s, 5s2, 4d10, and 5p3. All right, whoops, sorry, that's messy, 5p3. And then we also looked at ions. And we said that sometimes atoms have more or less electrons than you'd expect. If they have too many electrons, the atom gets a negative charge. And so that's called an anion, and we'll have to make our electron configuration a little bit bigger than what we would have otherwise. And if an atom has lost some electrons, it has fewer electrons than we would expect. And so we have to adjust our electron configuration according to what our needs are. So that means today's topics, okay, that is to say valence electrons first, and then exceptional electron configurations. These are a piece of cake. Let's do this fast, shall we? Valence electrons. Electrons found in the outermost PQN. Go back to the first page of your notes. See that the PQNs are 1, 2, 3, 4, 5, 6, or 7, corresponding to the first shell, second shell, third, fourth, fifth, sixth, and seventh shells, like in the Bohr model, but we're using the Schrodinger model. All right. So all you have to do is write down an electron configuration. What you have to do is find the biggest PQN. And if you take, let's say this, 2p6, the 2 is the PQN. Okay, the principal quantum number, PQN. Here, 3d10, the 3 is the principal quantum number. All we have to do is find the biggest number in this line. The biggest PQN. So is 1 the biggest number? No. Is 2 the biggest number? I see that there's a 2s and a 2p. Is 2 the biggest? No, that's not the biggest. Is 3? There's a 3. Wait. There's a 3s, a 3p, and a 3d. But no, I see bigger PQNs than that. I see 4s. Yep, but actually 5, I do believe. 5 is the biggest PQN here. So way out here, these are the electrons that actually participate in chemical bonding, and they're called valence electrons, the ones in the outermost PQN. So there are 2 valence electrons in this atom. How many total electrons are there? There's quite a few. Well, it ends in 5s2. I'm going to cheat. Look at my periodic table, and I see that this is strontium, SR, and SR has 38. Total electrons, 38. Count them if you want to. 2 plus 2 plus 6 plus 2, blah, blah, blah. It's 38. Unless I made a horrible mistake. Let's try this one. Find the biggest PQN. It's easy. Is 1 the biggest PQN? Heck no. Is 2 the biggest PQN? Nope. 3, 4, 5. Oh, I see 5 is the biggest one. But, oh, this is a little confusing because there's 5s and there's 5p electrons. So 5 is the biggest PQN. So all the electrons that are found here plus all the electrons that are found there. Okay, those are the valence electrons. So 5s2, 5p5. That means there's 2 electrons here. There's 5 electrons here. That gives us 7. How many valence electrons? 7 valence electrons. The s sublevel contains 2 electrons. And the p sublevel contains 3. 2 plus 3 is 5. 5 valence electrons. Exceptional electron configurations. What that means is sometimes atoms don't do what they're supposed to do. Scandium. Alright, scandium, it has an argon core, and it ends in 4s2 and 3d1. And is that what we would expect it to be? Sc ends in a 3d1. Yes, that's what we'd expect. Alright, you go right across the row. We're in the D block of the periodic table. Look in the middle of the periodic table, a little bit to the left. So we have scandium, then titanium, vanadium, chromium, manganese, iron. Alright, so they end up like this. Scandium has 2 electrons here and 1 here in the 3D. 4s2, 3d1. The next one, titanium, 4s2, 3d2. That's great. So far so good. The next one is vanadium, and it has 4s2, 3d3. So we had 3d1, 3d2, 3d3. That's great, doing great. And then the next one, chromium, should be 4s2 and 3d4. And oh boy, it's 4s1 and 3d5. It's done something weird. It's shuffled its electrons around. It took an electron from the 4s and put it into the 3d. Alright, well, we're not really going to get into why they do that. We just want to know that there's a few atoms out there that do not follow the rules that they're supposed to. Darn those atoms. So chromium is one of them. It would have, so I guess the way to say this in fairly simple terms is chromium would rather have, or it has a lower energy, if it has 1 4s electron and 5 3d electrons. In other words, the 3d boxes all have 1 electron in them. They're all half full. So up, 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 up with Huns is better than the alternative. We expect it to be 4s2, 3d4, but it's not. It's 4s1, 3d5. So that's weird. All right, we look at the next one, manganese. We're back to 4s2 and then 3d5. And iron, 4s2 and 3d6. That's great. Cobalt, 4s2 and 3d7. Nickel, 4s2 and 3d8. And then copper is another weird one. So copper is going to break the rules. It also has a 4s1, and it takes that 1 electron and puts it over here in the 3d. So the 3d is full. And so copper we would expect it to be argon core, 4s2, 3d9, but it's actually 4s, or argon core, and then 4s1, 3d10. So I guess what's happening here is, it turns out atoms really kind of like to have either half-filled d orbitals or completely filled d orbitals. They would rather have that more than they would like to have s orbitals be filled. So half-filled d orbitals, completely filled d orbitals seem to be happy states for atoms. So we're done for today. We did 2 things. The second thing that we did was we looked at some of these strange atoms. There's just a couple of them. So chromium and copper have exceptional electron configurations. They're weird, and not what we would expect. And then the first thing that we did was we looked for valence electrons. That is to say, electrons found in the outermost PQN. So write out your electron configuration, find the biggest principal quantum number. So 1s2, the 1 is the PQN. Find the biggest number there and find all the electrons that are found in that biggest PQN. Sometimes there's just 1 sublevel, like the 5s2. And sometimes there's 2 sublevels, like there's a 5s2 and the 5p5 in this case. If that's the case, add all the electrons together. And that was today's lesson. Thank you guys.